Hello everyone. In this lecture we start chapter 10 graphs and trees, and we begin with 10.1 graphs, definitions and basic properties. In order to introduce graphs, we start with the definition of a graph. A graph G consists of two finite sets, a non-empty set V of G of vertices and a set E of G of edges. So V of G represents the set of vertices of graph G, and E of G represents the set of edges in graph G, where each edge is associated with a set consisting of either one or two vertices called its endpoints. Later on, we'll see when an edge has one vertex at its endpoints and when an edge has two vertices in its endpoints. And then the correspondence from edges to endpoints is called the edge endpoint function. We'll see an example of this function later on. An edge with just one endpoint is called a loop. Okay, and two or more distinct edges with the same set of endpoints are called parallel edges. So if two or more edges have the same set of endpoints, we call them parallel edges. Also, an edge is said to connect its endpoints. Two vertices that are connected by an edge are called adjacent, and a vertex that is an endpoint of a loop is said to be adjacent to itself. An edge is said to be incident on each of its endpoints, and two edges incident on the same endpoint are called adjacent. So that's the definition of two adjacent edges. A vertex on which no edges are incident is called isolated. So that's the definition of isolated vertex. So in the previous slide, we saw the definition of a graph and a number of terminologies. So here, in order to illustrate all of those terminologies and definitions, we are going to see an example. Consider this graph. As you see, this graph has 6 different vertices: vertex V1, V2, V3, V4, which is isolated, V5, and V6. And also we have 7 edges: E1, E2, E3, E4, E5, E6, and E7. The question here is, write the vertex set and the edge set given the table showing the edge endpoint function. So the vertex set, as I said before, is the set of all vi's I from 1 to 6, and edge set is the set of all ei's I from 1 to 7. And here is the table for edge endpoint function. As I said in the previous slide, the edge endpoint function represents a correspondence from edges to the endpoints of those edges. So for example, the endpoint of E1 here, the endpoint of E1 is V1 and V2. That's why E1 corresponds to the set of V1 and V2 as its endpoints. In a similar way, we can see that the endpoints of E2 are V1 and V3. Why? This is E2. one endpoint of the edge E2 is V1, the other endpoint is V3. The endpoints of E3 is V1 and V3 too, and as you see in this figure, it's obvious that E2 and E3 have the same endpoints, so they are parallel. Because in the definition of parallel edges, we said two edges are parallel if and only if they have the same set of endpoints. Also, E4 has the endpoints of V2 and V3 in a similar way, and E5, which is here, has again two vertices in its endpoints, V5 and V6. However, edges E6 and E7 are a little bit different because they only have one vertex in their sets of endpoints. Why? Because E6 connects V5 to itself, so it's a loop, and E7 connects V6 to itself, so they both have one vertex in their sets of endpoints. So in part B of the same example, it asks us to find all edges that are incident on V1. In order to find all edges that are incident on V1, we have to take a look at this picture. On V1, there are three edges that are incident on. The first one is E1, the second one is E2, the third one is E3. Okay, then all vertices that are adjacent to V1, vertex is adjacent to another vertex if and only if they are connected with one edge. So V1 is connected to V3 and V2 using the edges E2 and E1 respectively. That's why V2 and V3 are adjacent to V1. Then it asks us to find all edges that are adjacent to E1. So in order to find the adjacent edges to E1, we need to find all edges that are adjacent, that are incident on V1, which is one endpoint of E1, and all edges that are incident on V2, which is the other endpoint of E1. So the edges E2 and E3 are incident on V1, and the edge E4 is incident on V2. So the set of edges E2, E3, and E4 are adjacent to E1. Okay, and then the next part of the question is find all loops here in this graph. In order to find the loops, we see that E6 and E7 have only one endpoint, so both of them are called loops. And then it asks us to find all parallel edges. So we know that E2 and E3 has the same endpoint, so both of them are parallel. And then the next part of the question asks for all vertices that are adjacent to themselves. So obviously V5 and V6 are adjacent to themselves because edges E6 and E7 connect V5 and V6 to themselves respectively. Finally, the question asks for all isolated vertices. As you know, only V4 is the isolated vertex of this graph because only V4 is not does not have any edge connected to it, or there is no edge that is incident on V4. That's why we call V4 an isolated vertex. Okay, so in this slide we continue presenting some other preliminary definitions regarding graphs. We start with the definition of directed graph or digraph. We say a directed graph consists of two finite sets, just like an ordinary graph. The first set is a non-empty set called V of G, which is the set of vertices of a graph, and a set D of G, which is the set of directed edges of the graph, where each is associated with an ordered pair of vertices called its endpoints. So the edges, the directed edges, are associated with an ordered pair of vertices called its endpoints. So in the directed graph, the endpoints are represented by ordered pairs, not by sets like what we had in previous slides. So if edge E is associated with a pair with an ordered pair like V and W of vertices, then E is said to be the directed edge from V to W. So since the edges are directed in a directed graph, we need to represent the edges with an ordered pair like V and W so that we can distinguish the start point of the edge, which is V, from the end point of the edge, which is W. As another definition, we define a simple graph as a graph that does not have any loops or parallel edges. So a simple graph needs to be loop free and it does not have any parallel edges, correct? In a simple graph, an edge with endpoints V and W is denoted by the set containing V and W. So obviously a simple graph is different from a directed graph. Why? Because in a simple graph, an edge is represented by a set of two endpoints V and W, but in a directed graph, we have an ordered pair like V and W to represent any edge of a directed graph, right? So a simple graph is also called a simple undirected graph. Means the edges have no direction. That's why we can represent them with a set. And if you remember, in a set, the order of elements does not create a different set. So I mean, the order of the elements does not matter, and by changing the order of elements, we cannot create new sets. So we see another definition here. This time we are going to define a complete graph. Let n be a positive integer, so it can be any number from 1, 2, 3, and greater. A complete graph on n vertices is denoted by k sub n and it is a simple graph with n vertices and exactly one edge connecting each pair of distinct vertices. So from what we studied in previous chapter, we can conclude that there are n choose 2, which is n times n minus 1 divided by 2 different edges in a complete graph. Why? Because in a complete graph, there is exactly one edge connecting each pair of distinct vertices. The question is, how many different pair of distinct vertices do we have in a graph with n vertices? The answer is n choose 2, or n times n minus 1 divided by 2. Let's see another example, example 10, 1, 9 of the book, which is about the complete graphs of n vertices where n is 1, 2, 3, 4, and 5. As you see here in the left hand side of the picture, we have K1, which is a complete graph of size 1. As you see, this graph has only one vertex and no edges. K2 has two vertices and exactly one edge. K3 has three vertices and three edges. K4 has four vertices v1, v2, v3, v4, but it has six different edges connecting each one of these vertices to another. And K5 has five vertices and 10 distinct edges because each pair of the vertices in this set of vertices should be connected using an edge because K5 is a complete graph. So we defined a complete graph as a specific type of simple graphs. Here we define another type of simple graphs, which is a complete bipartite graph. Let m and n be two positive integers. A complete bipartite graph on ordered per m and n vertices denoted by this symbol k sub m and n is a simple graph with distinct vertices v1, v2 all the way to vm and w1, w2 all the way to wn, and that satisfies the following properties for all I and k from 1 to m and for all j and l from 1 to n. There are three properties that a complete bipartite graph on m and n vertices should satisfy. The first one is there is an edge from each vertex vi to each vertex wj. So the vertex is partitioned into two parts. The vertex set is partitioned into two parts. The first part is, or the first subset is v1 to vm. The second subset is w1 to wn. So the property number one basically says there should be an edge from each vertex of the first part to each vertex of the second part, from each vi to each wj. And the second property basically says there is no edge from any vertex vi to any other vertex vk. So it means that the vertices in one part are not connected to each other. That's the second property that a complete bipartite graph must satisfy. And the last and the third and the last property is that there is no edge from any vertex wj to any vertex wi. Again, we have the same property that we mentioned in property number 2, which says there is no edge between the elements of one part, either the part v1 to vm or the part w1 to wn, right? So example 10.1.10 illustrate the concept of complete bipartite graphs. Here we show k 3 and 2, and here we show k3 and 3. In k3 and 2, the left hand side set of vertices are v1, v2, and v3, and the right hand side set of vertices are w1 and w2. So the size of the left hand side vertices is 3, and we have 2 vertices on the right hand side. As you see, none of these 3 vertices on the left hand side are adjacent to each other, and none of the vertices on the right hand side are adjacent. But between any vertex in the left hand side and any vertex in the right hand side, there is an edge. In the similar way, you can find K3 of 3 on the right hand side of the picture. As you see, we have 3 V's and 3 W's. None of these V's are connected to each other, none of these W's are connected to each other, and every V is connected to a W using an edge. Okay, so the next definition is a definition of a subgraph. We define this subgraph of graph G in the following way. We say a graph H is said to be a subgraph of graph G if and only if we have a number of conditions. First, every vertex in H is also a vertex in G. What does it mean? It means that the vertex set of H is a subset of the vertex set of G. What is the next condition? Every edge in H is an edge in G. What does it mean? It means that this edge set of H is a subset of the edge set of G. What is the next condition? The next condition is every edge in H has the same endpoints as it has in G. So it means that the edges in H have the same endpoints as they have in G. So let's see an example of subgraphs. In this figure, as you see, we have a graph of vertex size 2 and edge size 3. The set of vertices are V1 and V2, and the set of edges are E1, E2, and E3. So we have 11 subgraphs for this graph G. In this figure, we can see the first one, which only has V1 and it has no edges. You can see V2, the second subgraph, which only has V2, the third subgraph, which has 2 vertices but no edges, the fourth one, which has both vertices and 1 edge, E1. The fifth one is both vertices and only 1 edge, this time E2. The subgraph number 6 has vertex V1 and an edge E3, which connects V1 to itself. In subgraph number 7, we have vertex V and edge E3 connected, and we have another vertex V2, which is isolated from V1. In subgraph number 8, we have 2 vertices and 2 edges, E1 and E2, that both connect V1 and V2. In the ninth one, we have all the edges and all the vertices except edge E2. In subgraph number 10, we have every edge and vertex of the original graph except E1, and the subgraph number 11 is the original graph itself. So always remember that a graph is one of the subgraphs of itself. So a graph is a subgraph of itself. That's an important point. So here we have one more definition. We say let G be a graph and V be a vertex in this graph. The degree of V, which is denoted by deg of V, equals the number of edges that are incident on V, with an edge that is a loop counted twice. So if we have a loop edge, it is counted twice. The total degree of G is the sum of the degrees of all the vertices of graph G. So let's see this figure. We have a graph of vertex size 4, and let's assume that we are going to find the degree of this vertex. As you see, there is one edge incident on this vertex. There are two, there are three, and there is a loop that is incident on this vertex. So the total degree of this vertex equals 1, 2, 3, and for this loop we need to consider it twice, 4 and 5. So let me write it here. We have 1, 2, 3, 4, and 5 edges incident on this vertex. As a result, we can say degree of this vertex equals 5. So there's a very interesting theorem called the handshake theorem, which basically finds the total degree of a graph. It says if G is any graph, then the sum of the degrees of all vertices of G equals twice the number of edges of G. Specifically, if the vertices of graph G are V1 to Vn, where n is a non-negative integer, then the total degree of G is equal to the summation of degrees of Vi, I from 1 to n. And so this summation is equal to 2 times the number of edges of graph G. So that's a very famous theorem that basically says the total degree of graph G is equal to 2 times the number of edges of graph G. And a very direct conclusion of this theorem is corollary 10.1.2, which basically says the total degree of a graph is even. Why? Because it's equal to 2 times an integer. As you see, the total degree of G is equal to 2 times an integer, which is the number of edges of graph G. So the proof is very easy for the corollary 10.1.2, but we did not prove the handshake theorem, although you can find the exact proof in the book.